Hi, welcome to the solutions to function sheet 2, and what motivated this sheet was these questions at the bottom. In my introduction to proof course, I ask, so we proved that we've got, the setup is f and g, f from x to y and g from y to z are functions, and in the course I proved that if f and g are injective, then the composite g composed with f is injective. And on the problem sheet I ask, is it true that if G composed with F is injective, then F is injective? And is it true that if G composed with F is injective, then G is injective? And one of those is true and one of them is false, it turns out. And we proved the true one in the previous sheet. And so let's prove the false one. And to prove, let's disprove the false one by writing down an explicit counterexample. And to make that, we're going to have to make some explicit types. So the counterexample we're going to talk about is that we need, what do we need here? We need functions, we need sets x, y and z, or types x, y and z as Ling would call them. And we need functions from x to y and functions from y to z. And what we're going to do is we're going to let x have one element called a, we're going to let y have two elements called b and c, and we're going to let z have one element called d. So that's the setup. And then we're going to have f from x to y, and we're going to define f. So it turns out that when I say x has got, so this just means this is how you build a set with one element, and this is how you build a set with two elements. But strictly speaking, the elements of y turn out not to be called b and c. Their full names are y dot b and y dot c. And so I define a function from x to y by saying that a goes to b. And I define a function from y to z saying that both b and c go to d, unsurprisingly, given that d only has one element. So there's f and g. And if you then think about it, then f composed with g, it sends, it's a map from x to z, and x and z only have one element each, so it's a bijection, it sends a to d, which is certainly an injection, but the map from the map G from Y to Z is not an injection, because both B and C get sent to D. So that's going to be a counterexample, to this question. That's going to be a proof of this statement here, which is the problem sheet question with a not stuck in front of it. But before we start on it, I just want to say a little about how one proves sort of completely intuitively obvious statements. Like B is not equal to C, things like that. So the first thing I'm going to show you is how, given an element of Z, I'm going to prove, it says no, I shouldn't be saying that, let's do that. Given an element of Z, why is that element equal to D? Right, so there's a question. I've got an arbitrary, this says Z is an arbitrary element of capital Z, and how am I going to prove that it's D, which is the only element of capital Z? And you can do it with the cases tactic. If you do cases on Z, it will do with all the cases, and there's only one case, you see. I know that little z has got type capital Z, but the thing is capital Z has only got one constructor. So if I do cases on Z, it will reduce to that one constructor case where little z is replaced by z dot d, and now of course the proof is REFL. And similarly here, there's another trick with cases. How do you prove that B is not equal to C? So we do intro H, and now we've got to prove something false. But we've got this false hypothesis. The false hypothesis is y dot b equals y dot c. And again, it turns out that you can do cases, because equality is an inductive type with one constructor, and that constructor can never be can never give anything with that output, because somehow internally Lean knows that b and c, cases H works, right? That's what you need to know from this. But if you want to know why, then it's a rather elegant exercise in the theory of inductive types, but I'm not really too bothered about that here. Let's just observe that if we have a rubbish statement like B equals C, we can do cases on it, and it will solve an arbitrary goal. So these are the main two things we're working on, and so you can see here we want to prove G composed with F is injective. The point is, how does this proof go here? We've got to prove that this is not true, so let's do intro H. And so not x means x implies false. So now we've got this hypothesis that for all types x, y, and z and functions f and g, if g composed with f is injective, then g is injective. So we can specialize. This, right? H is a function, right? H is a function that eats. So first of all, it eats some sets x, y, and z, and then it eats some functions, which can be f and g. And then the next thing it eats is a proof. It eats a proof that g composed with f is injective. And so if we were just doing this, by itself, we don't have that proof to hand, but we can just feed it g composed with f injective there. And now we've got a, now H has finally become the false statement that G is injective. So, I mean, proving a false goal is normally difficult, but if you have a false hypothesis, then it's going to be okay. So that's why we're proving GF injective separately, because it's just sort of a convenient way to feed something in here. So let's try and prove that G composed with F is injective. So G composed with F, what is G composed with F? Let's have a look. It's a map from X to Z. So to prove it's injective, we need to do sort of intros x1 and x2, and then the hypothesis. So we know that g of f of x1 is g of f of x2. We don't even need that hypothesis. We've got to prove that x1 is x2, but x1 and x2 are elements of x, right? And x has only got one element, so if we do cases x1, then you see x1 says, okay, that used to say x1, but the only possibility for x1 is x dot a, I mean a or x dot a, given its full name, so case is x2. And now we've got to prove x dot a is x dot a, so we can do that with REFL. If we type it correctly, there we go. And in fact, we could probably have done, we could do sort of done rintros. When you do intros and cases, yeah, there we go. So there's an even shorter proof. Perhaps I should, I mean, that's kind of nice and obscure, but maybe I should just go back to there we go. So there's a proof that G composed with F is injective. And now what have we got here? We've got this hypothesis that G is injective, and we need to prove false. So let's specialize H. Let's specialize H at, let's put underscore. So we can see, right, so it was expecting, I'm quite surprised by that. It was expecting, I don't believe it is. Let's do y dot b. That's going to give me an error. Yeah, rotten luck. That's interesting. I'm quite surprised that that's happened. So let me unfold injective at H so we can really see what's going on. So H says for all A1 and A2, if G of A1 equals G of A2, then A1 equals A2. And so we want to, A1 and A2 are elements of, you see, the point is we want to get something false. We want to change H into a statement which is definitely false. So we want A1 and A2, Y is the one with two elements, right? Y's got elements B and C. So we want A1 to be B and A2 to be C. And then we want to insert a proof that G of B equals G of C. Okay, so what we're missing here, we want to have H. I claim that G of Y dot B equals G of Y dot C. That's what we're missing. And now let's just sorry that for a minute. And now I think I should be able to specialize. Oh, no, I've got two H's. Let's call that HG. Let's specialize H at HG. Oh, there we go, that's worked. And now I've got to prove, and now you see we've got this Y of B is, H says Y of B is Y of C, which isn't true, so we can do cases on H. And that's solved the goal, but now we just have to prove that G of YB is G of YC. And G of YB is defined to be D. G of B is D and G of C is D, so both of these are by definition D, so I suspect that this will be REFL. It is. There we go. So there's a solution to that problem sheet question. And now let's try this one. So again, so I should say it's the same counterexample, right? The question is it true that if G composed with F is surjective, then F is surjective? And in the setup above, G composed with F is this map from X to Z. X and Z have got one element each. And so the map between them sends A to D, it's obviously surjective. But F is not surjective. Because why not? Because F of A is B, so C doesn't get hit. So this statement here is not true that for all x, y, and z, if G composed with F is surjective, F is surjective, and that's why there's a not in front of it. So we can intro H again, because the definition of not x is x implies false. And then specialize G at x, y, z, F and G, and then let's put an underscore. And now we've got two goals. So we should do this. There we go. Let's pretend we're proper programmers, not just mathematicians. And now, so what have I got to do here? So I've got to prove that G composed with F is surjective. I can just clear H, so H has got nothing to do with this. I've got to prove that G composed with F is surjective. So what does that say? G composed with F is a map from X to Z, so it's intro Z. And I've got to prove that there's an X such that G of F of X is Z. You see, I just want to do rintro pointies instead. Because I do intros. What am I going to do here? I'm going to do intro Z and I'm going to do cases on Z. Rintro pointies. I have to prove that there exists an A such that G of F of A is Z dot D. So I'm going to use X dot A. And then this is F of X dot A is whatever it is, but then G of that is, so this is going to be refl. It is. So there's that. And now what's left? I've got one left. I've got to prove false, and so hopefully H is a false hypothesis. So H says for all, where does F go? F goes from X to Y. So H says for all elements of Y there exists an element of X such that blah blah blah, and that ain't true because F of A is B. So let's use C. So I want to specialize H at Y dot C. And then it says there exists an A. You see, this isn't true, right? So we can do cases on this, and then we do cases on H. And so now we have with A H A. So now we have A in X, and so now I can do cases on A, and then it will become there. So now we have F of X dot A is Y dot C, and that's not true. F of X dot A, hopefully it's not true. What's F of X dot A? Yeah, it's Y dot B. So HA says Y dot B equals Y dot C, so I can do cases on that. The case is HA, there we go. So that's proved that. And again here, this could be, I mean, let me golf this because it's going to be funny. So we don't need to specialize, we can just do cases at H, Y dot C. So let me do R cases this with pointy brackets A comma HA there. And then we did cases on A, but I can just do that here by just there. The reason you put nothing at all is that capital X has got, A is a term of type X, and capital X has only got one constructor, and that one constructor takes no inputs. So you do pointy brackets but with no inputs. And then cases HA, there weren't any cases here. So, oops, there weren't any cases here either, so I suspect I can do this. There you go. That's a rather nice proof, isn't it? Rintro this. Yeah, I mean, let's leave it like that. Oh, no, what have I done? There's not a proof. There, that's what I've done. It is a proof. We have no warnings and no errors. I'm constantly looking down here. I'm constantly checking for red underlines up here. And I'm constantly just checking down here just to check we have no errors. And indeed we have no errors, so there's a rather wonderfully obscure proof that it's not true that if G composed with F is surjective, then F is surjective.